a few example problems from the 5.3 practice. We're going to look at 3 of these, starting with number 2. So we've got the following reaction takes place at 75 degrees Celsius. We've got 2A to B, and we've got some information on some concentration and time data. And first thing we want to do is figure out what the reaction order is. Now, remember, we want to look at whether this is first, second, or zero order. Zero order, order. We're going to have concentration versus time as our straight line graph. If it's first order, that's going to be natural log of concentration versus time is going to be a linear plot. And then if it's second order, we've got the inverse of concentration versus time is going to be a linear plot. So first thing we can see as we are going from trial to trial, we've got increments of 500 seconds. The concentration is not changing at a constant rate. So we know that we can rule out, change colors here, zero order. So what we do want to do is we want to figure out whether we have the natural log of A or the inverse of A that's going to change at a constant rate. So we actually have more data here than we probably need. I'm just going to go ahead and plot out 4 of these. So I'm going to take the natural log of 2, which gives me 0.693. I'm going to take the natural log of 1.42. That gives me 0.35. Let's call that 351. Natural log of 1 is 0. Let's do one more. And then the natural log of 0.71 is going to be negative 0.342. Okay, let's go. Inverse of 2 is obviously going to be 0.5. Let's make that 0.500. Inverse of 1.42 gives me 0.704. 1 over 1 is 1. And then 1 over 0.71. Whoa, 1 divided by 0.71. Helps if I put it in my calculator, right? 1.41. Okay, so what we're looking for is how is this going to be changing from one to the next? So let's take a look at my rate of change here. Okay, if we go from 0.693 down to 0.351, that's going to be a change of about 0.342. Here, it's going to be 0.351. And then obviously here to here is going to be 0.342. Okay, so not perfect, but that's pretty consistent. Okay, if I change my colors here and I look for my changes for each of these increments, here 0.5 up to 0.74, maybe 0.204, 0.704 up to 1 is going to be 0.296, and then 1 to 0.41 is going to be 0.41. Okay, so what we can see is that we have a constant or a steady rate of change for our natural log of concentration versus time, which tells us that this is going to be a first order reaction. That's going to be natural log of concentration changes at a constant rate. Therefore, ln of A versus time will be linear. Okay, great. So that's one type of problem that you're going to be asked to do with integrated rate law. okay, using data to figure out the order. All right, let's skip on to number 5. I like this question. Cyclopropane is converted into propene via the reaction below. All right, at 750 Kelvin, the K value is 0.00018 seconds to the negative first. If the initial concentration is 0.51 molar, how much will remain after 55 seconds? Okay, this one is great because we have a little clue in here. And that clue is our unit on K. The unit on K is seconds to the negative first, which is going to let us know that this is going to be a first order reaction. Okay, remember the units on K are going to be molarity to the negative n minus 1 times seconds to the negative first, or time. And in a where n is our overall order, if our overall order is 1, 1 minus 1 equals 0. So that molarity goes away altogether, and we're just left with seconds to the negative first. So because this is a first order reaction, we can see that from here. Okay, we can use ln of A t minus ln of A initial equals negative kT. That's our integrated rate law for first order off of our equation sheet. Now, I like to do all of my algebra first. So if I am solving for the natural log, or I'm really solving for my concentration, I want to go ahead and add that ln of our initial concentration to the other side. So I'm going to find natural log of concentration at our time is going to equal negative kT plus ln of A initial. Okay, so I'm going to plug this in. Here I've got negative 0.00018 seconds to the negative first, or 1 over seconds, times 55 seconds, plus the natural log, of 0.15 molar. Okay, I'm going to move this up here for my work. All right, let's go ahead and do this math. Negative 0.00018 times 55. When I do this, my units of seconds will cancel. Okay, plus the natural log of 0.15. And here I get negative 1.90702. Let's take a little extra sig fig here. Okay, so if I'm going to find the concentration of A at that 55-second point, I'm going to take an inverse natural log of that value, negative 1.90702. This is a point where I like to use the answer button in my calculator to help me out, so I don't have to type all that back in. E to that answer is going to give me 0.149 molar, which really looks like we want to round this to 2 sig figs. So it's really going to be 0.15 molar. That 55 seconds really isn't enough in this situation to even change that concentration significantly with our number of sig figs. Okay, going to do one more of these, and I'd like to do number 8. Okay, a certain first order reaction has a half-life of 20 minutes. We want to calculate the rate constant for this. We know from our equation sheet that T1 half for a first order reaction is going to be 0.693 divided by K. So if we're going to find our rate constant here, again, I like to do my algebra first. Rearrange that to give me 0.693 divided by, divided by my half-life. So here, 0.693 divided by 20.0 minutes. K is going to be equal to 0.034, 3 sig figs. Let's make this 0.0347, and this is going to be minutes to the negative first as our unit here because our time unit is minutes, not seconds. Okay, the second part of the question is actually why I really wanted to do this one as an example, because this is a common mistake that students make. We want to know how much time is required for this reaction to be 75 completed. This right here, the 75 completed, is the part that trips students up. What we need to know, if it's 75 complete, that means that we have 25% remaining. So that's going to be our concentration at our time. Okay, so we're going to use the integrated rate law for first order reaction. ln of A at our time minus the ln of A initially equals negative KT. Again, I like to do my algebra, so I'm going to have time equals ln of AT minus ln of A initial minus K, or over negative K. All right, so I'm going to plug in my rate constant. I can go ahead and do that first. Negative 0.0347 minutes to the negative first. And then my natural log of my concentrations, if I have 25% remaining, I have 100% initially. Doesn't matter what the actual concentrations are, we can use the percentages in their place. So I'm going to take the natural log of 25 minus the natural log of 100. I'm going to go ahead and do this stepwise. Natural log of 25 minus natural log of 100 is going to give me negative 1.386 divided by negative 0.0347 minutes to the negative first. Gonna go ahead and finish this off, and I get 40 minutes, exactly. 40.0 minutes. So again, with these problems where you have a percent that is completed, make sure you consider how much actually remains when you are solving these problems. Good luck on integrated rate law.